Are you ready? Is it all okay? Okay. So welcome back. We are now going to look into how to query denormalized data. And what do I mean with denormalized? I mean that it's nested and it can be heterogeneous. So we've just left MongoDB and document stores in that way. We saw that we don't have any query language here. We have an API, which is function calls in JavaScript or Python or any other language you want. I put this SQL cheat sheet, but that's only an approximation, right? But now I will explain to you why it's not possible to do everything in SQL. Some people make that mistake. They think that SQL is all you need, and they will be able to write everything in SQL. But that's actually not true. And in fact, if it is indeed the case that you can do everything in SQL, then probably you shouldn't be using a document store in the first place. You should be using PostgreSQL. Right. And there are cases in which you cannot use PostgreSQL, you cannot use SQL, and then that's a different architecture, either based on a document store and a data lake, but with a query language that is actually tailor-made for denormalized data. Okay. So this is where we are. Wow, you see, we are quite advanced in our stack. That's actually the last lecture concerning denormalized data and trees. Then we'll have cubes, we'll have graphs and so on. Hopefully time permits, but we are already very high on the stack. And user interfaces is not even part of the lecture. I don't know the first thing about how to design good user interfaces. Probably put a text box here and a button, text box here and a button there, but that's pretty much it, right? But query languages, yes, that I can tell you a lot about. So you already know data independence from before, right? Data independence is this idea that as the user, all you want to see is a data model, a logical data model with logical algebras, like the relational algebra in a query language, and it isolates you from the storage layer and how this is done and so on. So physically, you could have PostgreSQL when you write a SQL query, but the beauty of it is that you can keep the same SQL query. Maybe, you know, just like between Basel-Deutsch and Zurich or Schweizerdeutsch, you need to maybe make a few changes, right? But apart from that, you can just switch the backend and use, there is something called Hive running on HBase, which is, again, some large-scale data analytics database with SQL, but the language is almost the same, right? So you just keep the same logical level. Apache Spark also has Spark SQL. Again, you know, it might be a few things that are different from others, but more or less it's the same language. You can map that in Spark. Actually, it's mapped to RDDs, actually on the very physical level, but on an intermediate level, it's mapped to data frame transformations, right? And hopefully, I mean, I know that it can be a matter of taste. Some people actually love to write code like what there is below, but many people actually find it simpler to write in a query language. In fact, there is a use case. I mean, these APIs are useful, but these APIs typically are used by the people who implement the language, right? So they use these APIs, but the final user is going to just sit in front of the Jupyter notebook writing something like that, right? Okay, so you can also, if you use Python, of course, directly provide your SQL query in there. But you know that with this magic, the SQL magic, you can directly type SQL in there. It's going to do that for you. Okay. However, this is SQL, and SQL was invented in the 1970s for normalized and homogeneous data sets. No nestedness, normal form data, you know, homogeneous, no heterogeneity. And it's hitting its limits, right? Today, we have data that is completely heterogeneous. Maybe it was logged over 40 years with a schema that keeps changing, so it's not homogeneous. It can be nested because you want to pre-join in order to avoid the joins and so on. So it's hitting its limits, and this is where we have a problem if we stay with SQL. Because we go from flat homogeneous to nested heterogeneous. You can have extra values, missing values, invalid values, nested values. So of course, some of the SQL systems are going to address that, right? You can basically handle missing values by putting nulls in there. You can handle nestedness by extending the system with array types and object types called structs in databases. So PostgreSQL actually supports arrays and objects if you actually push it. But it only brings you so far because you actually start hitting a complexity issue. Even though it works in SQL that you can query nested data, it's very, very difficult. So this is why it's actually simpler to view the nested heterogeneous data sets as collections of trees, as I've already explained. Another reason for that is that if you don't, and you really try to hit it hard with a hammer and make it fit in a table or a data frame, if you want nestedness, then this is the problems you get. This is real life. This is what actually happens with Spark SQL. If you try to open the file above as a data frame, you will get a data frame. Yes, absolutely. But you're going to get a data frame with a string type, and here an int. Because what's happening is that it detects here at the schema detection that you have plenty of objects, but that breaks the whole thing because there's a string in there. So what Spark is going to do is that it's going to serialize everything back to a string. And this is not a JSON object. This is a string that contains the text of a JSON object. That's very important. These are all strings here, all strings. So now the burden is on the user to then build a query on top of that, but the user will have to parse back as an object, maybe get an error for Pythagoras, so the burden is back to the user. This is awful. As a user, you can imagine all the burden and the trouble that you're going to have trying to write additional code in Python or Java to then deal with a data frame like that. Who feels that? Right? This is calling for problems, basically, calling for trouble. The same goes here with arrays, that we have arrays everywhere, but we have here US and UK that are just strings. And what Spark does is that it pushes everything to a string. This is not an array. This is a string containing the text of an array, right? That's called the serialized array. This is really a string and you need to parse it back. Here, it's a different problem. It's that it's nulls everywhere. Just because there was an extra field in there, it creates a new column with plenty of nulls. And that also has its limits because you can only have so many columns, right? At some point, with too many sparse columns, it just doesn't work anymore. But this is only the start of the problems because maybe you're lucky and you don't have this kind of heterogeneity and all you have is nestedness, right? So then if all you have is nestedness, then yes, you can try to use SQL. You can try to use the SQL and the extensions that you have, the so-called lateral views, explodes for an array, the dots, for querying objects. But here too, it's going to work on a few simple use cases. If you play with simple use cases, you make it work. But when it gets more complex, this starts to be complicated, right? Who understands spontaneously what these things do, these queries here, right? It requires a cognitive effort, right, to understand what's going on here. The notion of lateral view, which is kind of a join with a projected version of the array laterally and so on. This is kind of tough. I mean, my brain breaks when I see that. What's worse is that in some cases, you end up writing that kind of SQL. That is actually just a query that tries to look in the GitHub archive, the commits by the first committer of every event. And that's the SQL query you need to come up with because of the nestedness in the data and how complex it is. Well, with a language that was designed for nestedness, this is what it looks like. And that's actually much smaller, but this is because the features of the language were specifically designed for denormalized data, right? So this is the motivation here that we have. And there are real world examples that actually do have these sort of issues. And this is one that we love to use in exams because it's a pretty good example of data set that has these issues. It can be exported. It's generated every hour. You have a new file in that data set. It's on GitHub. All of the push, commit, and so on. So everything that's happening is just archived. And you have one compressed JSON file per hour with plenty of objects that look like that. But the thing is, in total, you have more than 1,300 attributes distinct, but every object only has 100. So you see it's a bit sparse, right? Less than 100. 10% of the path, so what we call a path is, for example, foo.bar, blah, 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 that's a path. And if you look at that path in every object, they have mixed types. It's going to be an integer here, it's going to be a string there. Why? Because in 2014, they wrote it as an integer, and somebody in 2015 decided to change the schema and make it a string, right? But they are not going to recompute the past data. The past data is just what it is. So this is why you have these mixed types. And that is already a reason why you cannot import it in a data frame, right? And this is just a small example with 7.6 terabytes, 2.9 billion events. It keeps growing and growing and growing and growing as people use GitHub, right? So we have this language that I'm going to start introducing to you tomorrow that's called JSONiq. It runs on document stores, it runs on top of Spark, it runs on top of pretty much anything that deals with nested and heterogeneous data. It's just a language, so you can implement it. One implementation that was actually done at ETH is RumbleDB. There's 20 of your colleagues who are past students who worked on that, and we have regularly theses and projects. They keep extending it. So this is really done by the students here at ETH, free open source. So this is just for people to use. I can tell you a few words. You can just checking the time. I have a bit of time too. What is JSONiq? It's actually a fork of another language called xQuery. xQuery was a language designed to query SQL, what am I saying? To query XML, as the X indicates. Because I think that there's, I heard that in a seminar that back then, Niklaus Wirth said that the next cool language should start with an X. And of course, the next cool language was xQuery, so we are very lucky. But xQuery is very complex. Why? Because XML is very complex. So for a while, xQuery was developed. It's very popular in the publishing industry. It's extremely powerful. It has a lot of very good qualities. But what's more, xQuery was designed by many SQL experts, the same people that also participated in the SQL standard. So these are people with a lot of experience of SQL, and they know the limits of SQL. So they had exactly what the experience it takes to design a language that goes beyond that with nestedness and heterogeneity. And so this is a standardized language. It involved people from plenty of companies, Microsoft, IBM, Oracle, sitting in the working groups in W3C, which is the same consortium that standardizes HTML, HTTP, and so on. And this is just people sitting in working groups. Every week, they gather for 2 hours on a phone call, then meet from time to time and design this. This is years and years and years and years of work. Every time you think it's going to take 1 year, it takes 7 years. Because you couldn't imagine to get people to agree across companies with each their implementation. It's a lot of effort, but it's worth it because then you get a standard at the end. And if people use the same standard, it's interoperable. So JSONiq was born as part of that working group, was there for a few years, and then we started thinking, how do we get arrays and objects to work in xQuery? But what we had in mind was JSON. Because in fact, if you think about it, what is xQuery about? It's not about XML, it's about nested structures, heterogeneity, and JSON is that too. So we made a proposal saying, okay, let's take xQuery, get rid of XML and put back JSON. And this is what JSONiq is. And so we kept it alive because it was meant for being the simplicity of JSON. xQuery was still extended with arrays and objects, but with a different use case in mind. That's known as xQuery 3.1. The use case was more to have structures in memory, for example, to index XML. So because we wanted to keep the simplicity of JSON, we just kept it alive. And so this is why you have it, right? So this is just the history behind JSONiq that I'm going to show to you tomorrow. There are 30 plus languages. There's a new language every week. Whenever somebody figures out you need a language for this denormalized data, then they invent a new one. It keeps growing. But what I can tell you is that if you learn one language and you understand the features, you can learn any language. One day, I hope it will consolidate, just like SQL. SQL is undisputed. Nobody would even dare to introduce another language for tables. But here, the market has not consolidated yet. Right. So maybe in 10 years, people will agree on a single standard. It will be maybe have things in common with what you learn, but really I have the long term in mind, right? It's the pedagogy, it's the features of the language that I want you to see. All right, so I'm going to, I think, stop here if it's indeed, I think, almost 4. So thank you very much for joining the class, and tomorrow we'll dive into JSONiq and I'll show you how that all works. Thank you very much, and see you tomorrow at 9.